Did the health center give you some sort of written? No? Did they just tell you verbally? You should probably send them an email. You should probably email them and ask them to put something in your portal. Because I know there were several instructors with other students who want to see it in writing. Okay, let me go grab the dosimeters. I'll be right back. Oh, I did get it. Yes, I did get that. Sorry. No problem. Okay. Let's do attendance. I see Kingston, Doug, Trevor, Parker, Chase.
I'm online.
Online, awesome, thank you. Mason. Karina, I saw you were online. Darren, here. Brooke. Welcome back, Zach. Pine. Porter. I think Porter was going to be online. Okay. Susan's here. And Michael here? Don't see Michael. Okay. Okay, so a couple of announcements before we get started. Today and next week on Friday at 11, INL is going to be presenting in the nuclear careers class. And you guys are welcome to come sit in on both of those. Today, it's going to be a representative from HR, and he's going to be talking about the application process there. I highly recommend that you all plan on applying for an internship at INL over the summer. He's going to be talking about that. He's also going to be talking a little bit about how the process works for a job, because INL is very slow. And so quite a few of the students who graduated last May did not actually start working at the INL until August. And so they're slow. And so understanding kind of how that process works, what information you're going to have at each step, and how to work towards that job if the INL is the place you want to work. It's good information to have. But I would highly recommend that you try to sit in next week, because the operations manager for the materials and fuels complex is going to be talking to the class about what she wants to see when she hires an operator at MFC. So it'll be a lot of good information. It's this classroom at 11 on Fridays.
Will those be recorded at all if we have a class at that same time?
I'm planning to record them. And just so you guys know, I got our YouTube channel, Zoom integrates with YouTube, working. So instead of having to send you the videos or upload them when you ask for them, you can just get on YouTube and watch all the videos. I'll broadcast them live, just so you know. And I think I emailed everyone a link to that, right? The channel. I think I did. If not, I know I sent it. No, okay. Then I might have just emailed the second years, and I'll send it out to you guys. And then third, did you guys all see the email on the training that's happening at Chernobyl? Okay. Yeah, super exciting. I'm very excited to get to go. So just so you know, we're able to go. The College of Technology is going to provide a partial scholarship to 2 students. But Ukraine currently has its borders closed to American citizens. We have a work permit because of the training. So we're technically on that exemption list. I don't know if we'll have to plan to arrive a day early and pay for our own hotel for 24 hours to do the testing that they're requiring people to do. They're expecting an announcement from the Ukrainian government. Well, they expected it Wednesday. So hopefully very shortly, announcing that they're going to lift that ban at the end of this month, which would mean we're fine for October. But it is possible that it would be postponed. And if it is, that just gives those of you who maybe don't have a passport already a chance to potentially apply.
So can only 2 students go, or is the partial scholarship only for 2 students?
Partial scholarship is only for 2 students.
Okay.
I suppose if you wanted to pay for yourself, you could go, but the course is $2,500 plus airfare.
Yeah.
So
How much is, or how long do we have to get the application in?
I need it by Wednesday.
I already have to almost.
Okay. yeah, it's a very exciting opportunity. So, okay. So today we're going to talk about dosimetry. Okay, you guys see that presentation online? Pop up for you?
Yeah, I can see
Yes,
it.
ma'am.
Awesome. Okay. So we've been going through GERT and we've been talking about radiation exposure and radiation protection programs. The measurement and calculation of radiation dose is called dosimetry. Okay. This service is performed by health physicists, radiation control technicians, RCTs, or health physics technicians, HPTs. Rich Bray down in the physics building teaches the health physics program here at ISU. And before they have let us tour their labs as part of our radiation detection and protection course. So you can kind of see this is done on campus because we have radiological facilities. We've got the reactor, we've got the accelerator center. So we can actually go see an actual working health physics lab and watch them process some of this dosimetry and do smears, which is kind of interesting. Per DOE and NRC regulation, the radiation protection staff should be given responsibility for selecting dosimeters appropriate for the conditions to be encountered. So we're going to talk about different types of dosimeters and different use, and I have a few that we're going to pass around and try to read and adjust. But know that as a reactor operator, it is not your job to read the dose off of these instruments or to analyze the passive dosimeters, and we'll talk about what that means, or select the right one for the environment. Your responsibility is to ensure that you are wearing the dosimeter that is assigned to you for the work that you're doing. But this is still really good information to understand why a particular dosimeter might be issued and how they work. Okay. 3 methods are commonly used to determine radiation doses to humans and vary depending on the type of exposure. Okay. Direct monitoring, which is also called personal dosimetry. This is used primarily to determine doses to individuals who are exposed to radiation related to their work activities. Indirect monitoring is using measured dose rates or airborne concentration of nuclear substances or using environmental pathways analysis. So indirect monitoring, we know you're around this material that gives off this kind of radiation and moves through the environment in this way. So therefore we can calculate that you would likely get this kind of dose. It's a calculation, not a measurement per se. Direct monitoring, we're going to put something on you physically that records the dose you're exposed to so we can exactly measure what radiation dose you received. And you can also have direct monitoring, 3 methods, that's not on your personal self, right? We have direct monitoring in portal monitors and radiation detectors that are throughout the facility. That's not personal monitoring, okay? Dosimeters specifically, so that's direct monitoring of personal dosimetry. They're classified into 2 general categories, passive and active. A passive dosimeter produces a radiation-induced signal, which is stored in the device, and the dosimeter is then processed and the output is analyzed. So we're going to talk about OSLs and TLDs. I have a finger dosimeter here that I'll pass around. This is a passive dosimeter. There is nowhere that you can see what your dose is. You have to wear this for a certain amount of time, whether that's a job or quarterly or for a particular activity. And then you give it to your HPT or your RCT, and they are going to essentially take it apart and analyze the dose that was deposited. Okay? Start passing this around. It's highly interesting. It's just plastic green, but we get to see it. Okay. Active dosimetry produces a radiation-induced signal, so same thing, except it's going to display a direct reading. So we practice with these when we put on our PPE. There's a screen here with an output, right? This is an active dosimeter. This is kind of the new style of electronic dosimeter. These have been around since the 70s, and it's still what we use at the reactor on campus. Essentially, all the engineers love them because you get to put them in your pocket protector, right? But when it records, you can look through the pin into the light, and there's a little graph in here, a little chart, and the blue line goes through the area where your dose is. So these are a type of very old-fashioned active dosimeter because you can get output from them. So start giving them a read. Yeah, look right up at the light.
The blue line is like how much?
Yep, that's the current dose.
It's 50.
Is that in milligrams?
The dose, the unit is at the top.
It's I don't know how to pronounce it, but RIM is part of it, right? It's part of RIM. It's RIM stands for that word.
Yes. So RAM is rotogen equivalent man. So it's essentially that dose in you. And we'll talk about doses in units in more detail. Yeah, this is Jennifer. She's one of the second years. She just asked if she could work on homework in the back of our class since she can't go in another classroom. Okay. Okay. Personal dosimeters offer a few advantages over other types of dose measurement, okay? Since it is worn on the person, it gives the best estimate of the actual radiation that you walked your person through, okay? So it measures the dose with no need for interpretation by the user. It's already interpreted. This is the radiation I walked through because this device is on me, right? But to be effective, you have to effectively wear your dosimeter, okay? It needs to be between the waist and the neck on the front of the torso and facing the radioactive source. This becomes important because certain types of dosimeters will have something called a beta window, right? Because betas can be blocked by a few centimeters of plastic, right? A sheet of tinfoil. So if your dosimeter is, for example, underneath your clothing or facing your body instead of facing out at the radiation source, it's possible that how you're wearing it will block and shield it from some radiation being deposited in that dosimeter. And you don't want that because then by how you wore it, you don't have the correct information about the radiation that you were in order to calculate your dose, right? So making sure that you follow the procedures for how to wear your dosimeter and each type is extremely important. Okay?
Is there a penalty for wearing a dosimeter wrong if you don't get an accurate reading whatsoever?
So if someone notices that your dosimeter is wrong, they'll usually remind you, hey, it has to be in this area and it has to be facing out. If it's something you repeatedly do, you could get written up for violating radiological control processes, right? And if you did not have your dosimeter on correctly and we're in a situation where either a regulator is doing an inspection and notices that, the whole group you work for is going to be written up for bad radiological control processes. And if you're unlucky enough to be wearing it incorrectly when an accident occurs and you actually really need that reading, that's going to be something that's going to be officially in the report that, like, well, this person can't get a dose because they don't know how to use their dosimetry, right? So then they'll use those indirect methods and they'll assume, hey, if you were standing by people who got this much dose, you probably did too. But the main driver is that you want accurate information about your own dose, right? Because that's a risk you're taking. You want to know that you're staying well below the safe levels of exposure, right? Okay. There are two types of radiation exposure, okay? External and internal. External exposure occurs when the radiation source is outside the body and the radiation strikes our body, okay? Internal exposure occurs when the radiation is emitted by nuclear substances inside the body. So if we inhaled an alpha particle, like we've talked about, it gets stuck in the lungs because it's blocked by such just a few cells of tissue. The dose that our lungs will receive is an internal exposure. If you were to swallow radioactive material or have it injected, which is, so I think the Hulk had an external exposure, right?
But then his dad injecting him with stuff when he was a baby, that's why he was
Okay, I guess I'm not as up on my Hulk history.
I
There's
assume.
a lot of different.
That's what I'm saying.
Okay. So I was going to say, if you have it injected into you like they do for medical treatments, or if you swallow something like for thyroid testing, that would be an internal exposure.
So is the cobalt-60, is that what they use for chemotherapy?
Cobalt-60 is typically used for blood irradiation and as a gamma knife. So chemotherapy, it can depend on where the cancer is. Because like we talked about, radioactive iodine uptakes into the thyroid, right? So my mom had thyroid cancer. She received chemo and the isotope was radioactive iodine so that it would go favorably to her thyroid and not irradiate the rest of her body, right? So she could specifically target those cancer cells. They have similar isotopes that are if you have certain types of blood cancer, and I think they also have some that target lymph nodes. I'm not certain exactly, but different isotopes will have more favorable uptake in different parts of the body. And then there's some that just kind of, well, we can't target it. We're going to just irradiate the whole body and hope we kill the cancer first. Okay. Personal dosimeters are used to measure external radiation. So when you wear one of those pen dosimeters or a finger dosimeter or this electronic dosimeter, what it's measuring is the material that's outside your body that's striking your body. It is not going to measure anything that you inhale or ingest or inject. Okay? For internal exposures, there's two primary techniques. The measurement of the presence of the nuclear substance in the body. And so when you have that in your body, they'll put you through some sort of very sensitive portal monitor, which is going to take counts through the whole body, or measuring the nuclear substances excreted by the body. We already talked about my friend who had to collect his urine and fecal samples for analysis. That's the primary ways. Okay. When we're talking about external dosimetry, we're worried about radiation that can penetrate the skin. So beta, photon, which is also beta, neutron, and gamma. So photons and beta interact through electronic forces, right? and neutrons interact with nuclear forces. So how we detect our our beta, gamma, and neutron sources is going to be different between each type of radiation that we're trying to detect. Okay? Dosimeters worn on the torso are often called whole body dosimeters because essentially they're on the bulk of your mass and they're meant to detect what you walk the bulk of your mass through as far as radiation, right? So they're going to be your whole body. There are also dosimeters worn on the extremities. So we passed around that ring dosimeter. If you are working at a shielded glove box and there's a large amount of shielding over the main part of your torso, it's highly unlikely that your dosimeter, your whole body dosimeter, is going to pick up any significant dose because you won't get a large exposure. But your hands are going to reach through that shielding inside the gloves and handle the material, right? And so even though we have lead-lined gloves that also provide shielding, oftentimes glove box workers will wear an extremity dosimeter in order to measure that elevated dose you might get reaching your hands into the radioactive environment. You can also wear them near the eye. We talked about how the lens of the eye is sensitive to radiation. And so sometimes if you're in a certain type of radiation field, they might put one near your face or your eyes to see if there is an elevated dose that might have gone into the lens of the eye, because there's a lower limit on what you could receive to the lens of the eye versus the whole body. Okay, when your health physics staff choose the type of dosimeter for you to use in a particular application, they're going to have several things that they're going to consider. Energy dependence and angle dependence. What this is saying is not all radiation comes off of a source at the same energy. Sometimes it's going to move further in air. Sometimes it's not going to move as far. And so the energy that's coming off is going to affect how well it's deposited on your dosimeter. And so if you have very low energy sources that don't have their particles travel very far, you want a different dosimeter that can get that very low level versus a dosimeter that's meant to receive very large amounts that may not pick up something that low. But you don't want to take your low level dosimeter into a very high energy radiation source because it might be overwhelmed, right? It can't discriminate and give you any useful information because it's just too much, right? Angle dependence is essentially saying that they want to design a dosimeter so that even though we have 360 degrees that we could receive radiation from, you're going to not have dose blocked by the angle that you face the radiation source by, right? So if I'm standing here and talking to you and I had a source with, our guy with PPE, I want to know that I'm getting a good and accurate dose count, even if my dosimeter isn't facing that source, right? Because that radiation is going to come out, it's going to bounce off the surfaces. I'm still in that radiation field. So regardless of the angle that it's coming at me, the dosimeter needs to record it well, okay? Dosimeters vary based on the type of radiation to be detected. We discussed this, whether it's alpha, beta, gamma, or neutron, right? And an important thing to note, is alpha an external or internal hazard? Do we use whole body dosimeters to detect internal hazards? No. So you're not going to have a dosimeter that counts your alpha. Okay? Fading. You don't want to have to count a dosimeter every single day, but you also don't want to leave it so long that any of the information on your dose over a period of time is lost, right? At INL, they're going to process dosimeters quarterly. So that dosimeter has to actually be able to store the information about the radiation that you received for 3 months, right? The ability to be reread. Certain types of dosimeters, you take them apart, you read the information, that's it, they're done. You have to replace it with a completely new one. And so if you mess up that reading, you've destroyed the record. You can't get that information back, right? Other types retain their signals and you can process them more than once. So you have the ability to go back and get that information again if you make a mistake. And this can have pros and cons as far as expense and record keeping. But in general, one use, one loss is not the preferred method. Okay? Your limits of detection, right? The lowest dose that can be measured. Sometimes you need a more sensitive dosimeter. Sometimes you need to be able to detect lower quality of radiation dose. And then operators really care about ruggedness and ease of wear. All of these things are the health physicist's responsibility. But if you can't actually wear your dosimeter and do the job you're supposed to do, it's going to be falling off. It's going to be caught on equipment. It's going to be impossible, even if you're trying your hardest to get an accurate reading, if it simply can't stay attached to your PPE as you go into a radiation area, right? So the form factor has to be appropriate. Okay? Typically, a dosimeter is a detector inserted in a holder. So this electronic dosimeter would not be very typical at a nuclear power plant. But now that it's in a holder, or we use those plastic bags, I can take it with me, and I can get information on my dose, right? This particular dosimeter is actually more commonly used for emergency responders. So military response to radiological or nuclear incidents like the Army Bs, firefighters who typically have the hazardous material responsibility for a city may also have an electronic dosimeter like this in Utah. I think nearly all of the Salt Lake Police and the Utah State Patrol carry dosimeters, just because theft of the construction sources is so common. And after 9/11, there was a huge push by the Department of Homeland Security for police officers and first responders to have this capability in case there was ever some sort of RDD, a radiological dispersal device that was used by terrorists. I think it's not as big a priority anymore as it was, but for a while, everybody was trying to give everybody one of these. Okay. In general, the detector contains the sensitive elements and the holder contains any filters that are used. So the holder might be a piece of plastic that automatically filters out alpha by simply being plastic, right? Okay, we're going to talk about a couple of common types. Thermoluminescent dosimeters, TLDs, are the most common type of dosimeter in use. They work using thermoluminescence. So when ionizing radiation passes through the detector, the atoms are going to release some of their electrons in this chip, okay? The electrons eventually become trapped within purposeful impurities in that detector, and then they remain trapped there until we heat it. This is the thermal part, right? When we add heat to this detector, the trapped electrons leave their excited state, return to the ground state, and as they do that, they emit visible light. The amount of light emitted at a particular temperature, called the glow curve, and a health physicist can take that glow curve and calculate your dose. So these are relatively inexpensive. They are easy to use. They are extremely common. And this was the first type of dosimeter I ever had, was a TLD.
And they reheat it multiple times just to see the visible color.
No, once you heat it, they drop out of their excited state. So this is a single read. So the improvement, and something that INL has adopted, are optically stimulated luminescent dosimeters, OSLs. They're very like the TLDs. Sorry, this is a typo. It's just OSL. The major difference is that the luminescence is produced by hitting the OSL with another light beam instead of heating it up. And so you can reread this because you're simply passing a light beam over it, and then that causes a reaction that you can repeat, okay? OSLs and TLDs are both passive dosimeters. From the definition we talked about earlier, can someone tell me why they're passive dosimeters? Michael?
They read after it's been processed.
Exactly. We have to process them to get a dose. They don't give us a direct reading. So in contrast, we have direct reading dosimeters, or a type of active dosimeter, right? They display dose and dose rate. So I'm going to pass this around. On here, there's a button for dose and rate. When you press dose, it's going to give you a single number, right? So this is your, I think the unit right now is in millirem. So right now, since this dosimeter has been on, it has collected 2.7 millirems radiation, okay? When I press rate, or sorry, picorem, it's in picorem, it's going to tell me the rate of radiation around me right now at this time, which is 12 picorims an hour. So if I stood here for an hour in a 12 picorim per hour dose rate field, I would have a dose of 12 picorim. Okay? So it's giving you information about the level of the field you're currently in when it talks about rate, and dose is giving you the cumulative dose that you've received because of how long you've been in that field. I can also set the alarm so that if I walk into a radiation field that is too high level for the work that I'm doing, I can hear an audible alarm. And it's set way too high for us to hear the alarm right now. I'll have to play with that if we want to hear it, but it's a terrible trilling high pitch sound, so we won't. But I'll pass this around. Make sure you look at a rate and dose. It is important to be able to have both pieces of information on a direct read dosimeter, because the purpose of that type of dosimeter is to give you real-time feedback. So if you're doing some sort of job where you're next to a much higher radiation field than you should be entering, you need to know when you've crossed that boundary, right? Or if you're working in an area where you might have an unknown radiation field, you want audible and visible, because you can see that dose rate feedback before you go into a place. If you're doing a task that takes a very long time, and so you might have to get a higher dose, you also want alarms that tell you as you're approaching that dose, so you know when you need to stop and place that work in a safe condition and let someone else come replace you. Something that happens occasionally in the nuclear industry is you will have a job that is going to cause people to get a very high dose. And so in order to not do that, in order to keep doses, ALARA, right, as low as reasonably achievable, they might break that task up into pieces. And so one person comes in and opens a valve and then leaves, and the next person comes in and starts the pump now that the valve allows the flow, and you switch. Have you guys seen the movie K-19, The Widowmaker, the one about the Russian sub? Okay, it's a great movie. It has great actors, and it's about a USSR nuclear submarine that has a horrible accident on its first voyage, and the response that the sailors tried to provide. And one of the things they do is there's an extremely high radiation field and they need to make a repair. And so they send a person in to start welding for 2 minutes. He comes out, the next person goes in. He comes out, the next person goes in. And they try to essentially not kill themselves because of the radiation dose by breaking it up into smaller tasks, which is in the movie not very successful. It's a very sad story, but it's the same principle. We just do it with more data and less reactive than that movie portrays. Okay, neutrons are kind of their own thing. They will not typically be detected by your TLD or OSL. And if you're in a radiological facility that doesn't have the potential for a criticality accident, you don't need to detect neutrons, right? If you're in a reactor, the reactor is supposed to go critical. And so you're not looking at that neutron dose as the indicative of an accident. Whereas if you're in a facility that stores fuel, and we don't want criticality, we don't want a reactor not in a reactor, we want to make sure that we're monitoring for our neutron dose. These are slightly different. They essentially look at the reaction of neutrons with material in the reactor and the detector. This produces charged particles at the site of the interaction, which create tracks through the material as they move. And then you can essentially look at those tracks because they chemically etch through your detector material, and you can essentially count them in order to get information on your neutron dose. Certain facilities at INL have you wear this. Fuel handling facilities would have you wear this. It's just an extra piece that can be put in to a dosimeter or a separate dosimeter. Talking about neutrons, there's also usually portable neutron survey meters, typically placed in an area where radiation readings are the highest. And so in addition to your dosimeter, things like this would be placed so that you can integrate the dose rate over the period of time that the workers were in that area, and your dose can be estimated, right? And that portable neutron survey meter might be assigned to each worker if you have reason to believe there might be a neutron accident that you need to monitor for. Okay. Any questions? All right. We got through our GERT training and this little additional piece on dosimeters. There is a quiz that is specific to GERT, and that's that reading quiz 3. When you take that quiz, the questions that come from the GERT training, make sure you pay attention to what they're asking, because if you need to go get certified as having completed GERT, that's the same kind of questions that will be on your test. Wherever you go, whatever facility you're working at, this DOE training is the same, and NRC has one that's pretty much universal between every NRC regulated place. We don't do the GERT certificate because it would increase your class fees, and literally next semester you're going to get Rad Worker 2, and that's a far more useful certification. So we charge you the class fee to get that instead of getting a small step on the way, because you'll have that before any internships you would do. So, but if for some reason you had to go in the workplace and get GERT, pay attention to the questions that we ask on that quiz, because they're directly from INL's GERT questions for their certification test. Does that make sense? Okay. All right. If there are no questions, that's all I had for today. So we're done a little bit early, unless you guys have any questions. Yes.
Do you think 9/11 slowed down the nuclear energy field?
I don't think that it had a very substantial effect right after the incident. You know, everyone kind of got panicked, like, what if they had crashed a plane into a nuclear power plant? But due to the requirements for nuclear containment to withstand tornadoes and projectiles from tornadoes and hurricanes, they were already able to withstand a plane crashing into them. Like, that was already something they were built to handle. And the concrete that's used in containment vessels, you can find videos on YouTube of them putting a jet on a train track and accelerating it into the concrete walls that we use for containment. So it was one of those things that everyone got worried briefly, but the nuclear industry was actually able to say, hey, we've already considered this and designed for it. So I don't think it was that big of a setback. I think the biggest setback has actually been economics. And nobody wants to put the money into construction to actually build them. And what? Well, Fukushima now has been a big deal. Yeah. See you guys. Okay, I'm going to end the meeting for those of you who are online, unless you guys have any questions.
No, ma'am.
I don't have any questions.
Okay. Have a good weekend, guys.
Thank you. You too.